Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And within the playlist, I create little mini-series based on the different types of experimental designs. And this little mini-series, we're doing balanced two-factor factorial designs without interaction. Now this is part 2 of a 7-part mini-series, and we're looking at the column spaces of the design matrix. And matter of fact, I think the majority of this first page is so important. I actually wish I'd have introduced it at the very beginning of this playlist because it's so critical, so important to understanding the theory of experimental designs. But before we start, I want to revisit something in part 1 when we were talking about the means plot. And here we had a two-way additive model, which was here, and then I talked about the theoretical means of all the levels, and if we were to plot them, the lines would be parallel, and I said parallel-ish. Now parallel-ish refers to the sample means. The population means, if our model's correct, are exactly parallel. And what I meant to say, or should have said, is that within each level, the effect from going to, say, from B2 to B1 is the same as the effect from going B2 to B1 in each of the levels. So this difference is the same. So for instance, if we were to add, say, B4, which is really close to B1 here, it would still run parallel, and the effect from going from B1 to B4 in level A is going to be the same as going from B1 to B4 in A2. In the same way for A3, it's going to be really close, but it's going to be the same distance. So then this is going to be really close, this distance, and that would be B4. I don't know if I explained it well enough in part 1, so I wanted to revisit it. And all the lines should be parallel, and we estimate it what the sample means. Now on to part 2. And again, this is so important. So the model is x beta epsilon, so it's a linear model. Errors are normally distributed, mean vector 0, covariance matrix sigma squared I. We partition the design matrix into one x alpha and x beta. See part 1 for this, and the beta parameter is partitioned into mu, grand mean, the alpha parameters associated with factor A, and the beta parameters associated with factor B. Now here are the big notes, and you are so lucky that you're watching this video because this is absolutely critical to understanding the theory behind analysis of variance. So, and my first big note is I should have presented these the following ideas at the very beginning of this playlist of design of experiments, because it's absolutely critical understanding what I'm getting ready to say. Now, one note here, the next note is M, the perpendicular, well, M and I minus M, the perpendicular projection matrices onto the column space of X, and the column space of the orthogonal complement of the column space of X are vital in the development of the theory of design of experiments. And both are unique for a column space. So if you change X, but the column space doesn't change, M is unique. This perpendicular projection matrix, which means this perpendicular projection matrix is unique. And the next bullet here hopefully will drive that point home. So let's say we have two models. Now notice the y vectors are 100% the same, but the x matrices are different. And we have beta 1, beta 2, epsilon 1, epsilon 2. Now, but the column spaces of x1 and x2 are identical, but the actual matrices are different. Okay, and you might wonder, how in the heck can that be possible? Well, let's say in this model here, we center all the variables. So we subtract a constant from each of the variables, right? That doesn't change the column space, but the actual matrices are different, right? And so that could be the setting. And so when we develop the least squares estimates for beta 1 and beta 2, they are different because the least squares estimates depend upon the x that we use. So if we use, the uncentered model versus a centered model versus a centered and scaled model, the least squares estimates that we get are going to be different in each of those cases. And, and this really arises when the column spaces are not full column rank. But the fitted models are all equal. So this is the fitted model, x, least squares estimate for beta 1, x2 times the least squares estimate for beta 2, they're equal because we've shown that it has to equal my. And y is the same in both models, and the column space are the same, so the perpendicular projection matrix onto the column space is m. This is unique. So this has to happen, and this has to happen, so that implies that those two. So the fitted models are 100% unique. And it seems like whenever I do a video, the cat starts meowing. So the estimate of the error variance is also the same in these models, right? The estimate of the error variance is y transpose I minus m y divided by the rank of I minus m. So what in here is not unique, right? The y's are the same. M, the perpendicular projection matrices, are unique for a given column space. So that says the estimate of the error variance is the same. Also, estimable functions are unique. Remember, estimable functions mean a linear combination of the beta parameters. So let's assume that lambda 1 beta 1 is estimable, right? This is a linear combination of these betas. It's estimable if and only if it can be thought of like this, right? That lambda has to be part of the row space of the design matrix. This is for some row, right? But then lambda 1 transpose beta 1 is equal to this. That's by definition, right? That's the expected value, the fitted model. But remember, this is just x1 beta 1, but that is equal to x2 beta 2, right? We just said that up here. Those two have to be equal. But then that means lambda 2, where it equals rho transpose x2 beta 2, is estimable, right? Because this is estimable, that has to be estimable. And essentially what it means is we're taking this, it's the same row space of the expected value of y. So that, and the unique value would be rho transpose my. So what we do in the theory of analysis of variances, we kind of manipulate the design matrix into a form that is very tractable, and that means mathematically tractable, and then we can understand the structure of a lot of the estimates and theory behind what we're doing. And so now let's illustrate it in more detail in this model. So we're back in the balanced two-factor factorial design without interaction, and so this is our model. So now the column spaces of the design matrix are this. So x star is 1, x alpha, x beta, just as we set up there. Now note that the column space of 1 is a subspace of the column space of alpha, right? If we add all the columns of x alpha, that actually equals 1. So this is part of that. And the 1 vector, is an element of this. So that's kind of saying the same thing. So that means that the column space of x alpha is equal to the column space of 1 x alpha, right? Because this is part of this, so it's redundant, so it doesn't change. But now we can use the Graham-Smith algorithm to make x alpha orthogonal to 1, and we do that by this. And notice that we're changing these columns here. And we're doing it by subtracting a constant vector, right? But in a unique way. It's this. So it's the column of interest minus the column transpose times 1 divided by 1 transpose 1 times the 1 vector. So this constant gets put on, in each column. And then that's our new X, right? And this is done for every column in X alpha, so 1 through A. So that means, so what we've done is this. We've taken the column space of 1 X alpha and transformed it into this. The column space are the same because we're only adding or subtracting a constant vector from each column. So these column spaces are the same, but we do that because 1 and X alpha star, this has been, I'm going to say Gram-Smitted, if that's a, they're orthogonal. So but the perpendicular projection matrix is unique whichever matrix we use, this matrix or this, augmented matrix. It is M alpha, which is X alpha transpose, X alpha inverse, X alpha transpose. That is the perpendicular projection matrix on the column space of X alpha, right? This was equal to this, but is equal to that, so they're all equal. Now we let J be the perpendicular projection matrix onto this column space. Yeah, the column space of 1. So then we let M alpha minus 1, it's the perpendicular projection matrix, into the orthogonal complement space, the column space of 1, with respect to alpha, i.e. this column space. So M alpha minus J projects things into here. Now J projects things onto here. They're orthogonal, so the column space of this is actually the addition of the two. So that means, but this is the perpendicular projection matrix, but, okay, so since they're orthogonal, the perpendicular projection matrix onto this is actually the addition of those two perpendicular projection matrices. This is onto 1. This lives in X alpha star, but it's orthogonal to 1. That's what this is. But when you add those, you just get M alpha. Well, that's what we were saying. Now, similarly for X beta, we're going to Gram-Schmidt it. We're going to make every column in there orthogonal to the 1 vector. And this is for I equals 1 to B. And maybe I should have used J, but it's just an index. So the 1 vector is in the column space of beta, X beta, which is equal to this column space, which is equal to this column space where every column in here is orthogonal to 1. And we let X M beta equal this, the standard way to create a perpendicular projection matrix onto that column space. And we let M beta minus J be the perpendicular projection matrix onto X beta star. This piece right here, so it's orthogonal to this. So then we can add those two perpendicular projection matrices and we just get M beta back. Okay, but now the column space of X star, that's our original design matrix, which is this, which is equal to this, right? So these column spaces are the same. We've just made these column spaces orthogonal to 1. And it turns out that these column spaces are also orthogonal. One's orthogonal to X alpha star, orthogonal to X beta star, orthogonal to 1. And I'm going to point you back to randomized complete block designs where we prove that these two are orthogonal. Let's let M be this perpendicular projection matrix, right? That's how we define it. But using this original design matrix, the structure of this, how would you ever get a handle on that? Well, the way we do it is we create another X that doesn't change the column space, but now each of these are orthogonal. So the perpendicular projection matrix onto this is actually the addition of each of those perpendicular projection matrices. And I actually have a video called The Sum of Perpendicular Projection Matrices, which I think is worthwhile to watch if you haven't seen it yet. So to get structure on this, so this is the perpendicular projection matrix on the column space of X star, we could use this column, this matrix, and then so M would be this projection matrix plus this projection matrix plus this projection matrix, which is this. So this is the structure of that perpendicular projection matrix. And then once we start grabbing or understanding structure, then we can understand the underlying theory and the formulas and everything underneath it. And so the last point is we changed the matrix, the design matrix X star, but not the column space, to create structure and formulas that are understandable. And these changes do not change the fitted values or the estimation of sigma squared or estimable functions. And so anyway, well, that's all I have for this video. Hopefully you hopefully you enjoyed that. I sure did. Please like it, subscribe so you don't miss the next one. Thanks, bye.